Hello, everybody. It's a pleasure to introduce Dr. Tianzi Dong. He's now at the Department of Computer Science and Technology of the University of Cambridge, and is going to give the first of 3 lectures in which he will tell us how we can make a transition from a pure deep learning towards not just symbolic, but neuro-syllogistic reasoning. And this is something that is coming from his recent paper that has been accepted and presented in Philadelphia few days ago. Thank you very much.
Thanks for the introduction, Pietro. So today I will start to introduce a novel neural network that reach the rigor of symbolic level syllogistic reasoning. And this is the follow-up talk of my last talk, which explains why a current machine learning method cannot reach the rigor of logical reasoning. And then the natural question is, what kind of neural network can reach that level? So a very brief recap. There are 4 methodological limitations that prevent the current deep learning system from reaching the rigor of logical reasoning. The first is the composition table cannot cover all valid type of syllogistic reasoning. And second, if we using training data, and these training data will automatically generate out of distribution data, so that the system will become indeterministic. And third is if we're using the end-to-end mapping to train a neural network, then this kind of end-to-end mapping will introduce contradictory features of object recognition model and logical reason model within this one-step mapping. And the fourth limitation is that normally when we see a neural network reaching a very good performance, we will assume these latent vectors encode the knowledge structure that people are using for reasoning. But this is not the case. In our case, our experiments show that latent feature vectors does not contain any geometrical structure of 2 circles. So let's go to the first limitation. Why the combination table cannot cover all type of syllogistic reasoning? The reason is among these valid types, there is logical conclusion and logical consistency. They have the same input. They have the same premises. So in this case, if all x are y, if all y are z, we can only construct one model. But we have 2 conclusions. One is says all x are z, it's Barbara type. The other is says some x are z, it's Barbary type, the weaker version. And combination table cannot cover both. So the first question is, how can we design a novel neural network to address both valid type of reasoning? For sure, I cannot say 2 conclusions share 100% confidence, and each is 50%. And it's just like tossing a coin, okay? So because they have the 2 premises determines one model, but we have 2 conclusions. So that we can look at the 2 conclusions. We can say each of them is like question the model from 2 different perspectives. They ask in different questions. When we say the conclusion is all x, y, they are asked questions, is sphere x inside sphere z? Okay, it's yes. Another weaker version says, does sphere x connect with sphere z? It's a weaker version, okay? So this means when we design a neural network, this neural network should separate model construction from model inspection. Okay, this separation will allow this novel neural network to cover all type of valid reasoning. Okay, in that case, we can say the OLANet, they first construct a model, and then with different type, with two different reasoning type, they correspond to different perspectives to inspect this model. Okay. So that in this way, we remove the first limitation, combination table. We can replace by reasoning through model construction and model inspection. Now, then we need to remove another third level. For the latent feature, because they do not encode geometrical relation. So we need to explicitly represent them into geometrical object. This means we separate object recognition from model construction. All right. So first is object recognition net. Import pixel images. This network will recognize geometric object. And then the reasoning, the first part reasoning is to construct a model from the premises. And then the inspect network is to see whether the conclusion is satisfiable or choose or satisfiable, unsatisfiable, valid or invalid. And we can remove all this. And then to remove this out of distribution data, because these are introduced by training data, this means if we want a network without hallucination or without out of distribution input, this network should not be using training data. How can we do that? And this is the main novelty of this neural network. The construction of a model is not by remembering what appears in the training stage. Okay. If we do this, then we solve all these limitations. And then we need to question how to construct this model without training data. Let's take example first. If say the input are some lawyers are present, no present are scientists, and the conclusion is some lawyers are not scientists. So we first replace them with geometrical relation between circles. Some lawyers are present means red circle and green circle are connected somehow. No present are scientists means red circle and purple circle disconnect. The conclusion, some lawyers are not scientists means the green circle is not inside the purple circle. Now, the model construct means the network should construct 3 circles to satisfy 3 relations. If they reach global loss 0, then the network say the conclusion is satisfiable because they construct model. But this conclusion is valid. Valid is much stronger than satisfiable. If we reach global loss 0, the network only can say the conclusion is satisfiable. It cannot draw a conclusion is valid, because valid means the negation of the conclusion is unsatisfiable. So we negate this conclusion. It becomes all lawyers are scientists. Then the network should show this conclusion is unsatisfiable, means it cannot find three circles satisfy these three relations. Obviously, it's very easy. Any kind of three circle, no matter how we use it, the global loss will be greater than 0. But this is not the reason say the conclusion is unsatisfiable. To prove unsatisfiable means no matter how many number of iterations, it will never reach global loss 0. And to come to this conclusion, we should enhance the criteria, say, for any satisfiable statement, conclusion, the network will construct a model within a maximum number of m epochs. And this m is a constant and should be proven without data. It's a feature of the network. Then for unsatisfiable statement, this network iterates m times and still cannot construct model, then it stops iteration and says that conclusion is unsatisfiable. And this feature is independent of data. And we need to prove this. Okay, that's the criteria for deterministic neural network for syllogistic reasoning. This means for any satisfiable syllogistic reasoning, a deterministic neural network can construct a sphere configuration of this Euler net, as this Euler diagram in the embedding space, reaching global loss 0 and maximum using m epochs. And this m is a constant number. Okay. So any question about this criteria? It's different from the current metrics. Current metrics, we collect data, the testing valid and training valid and test. Even it reach 100% accuracy, it does not reach the rigor of symbolic level of reason. Okay. So let's go through example to understand how to decide this reasoning is satisfiable. That is quite easy. We need the network just construct three statements become three target relation. All x are y means the x circle should inside y circle. No y are z means y circle disconnect from z circle. And some x are not z means x circle is not inside z circle. So network just need to construct three circle to satisfy the three relation, then it proves conclusion satisfiable. And to decide unsatisfiable, the network should first negate, this is impossible, unsatisfiable. It should, let's say, this is impossible, so he should first, oh, sorry. It should first, okay. It should negate his conclusion and says, after negation, the three statements are, you cannot find a configuration that satisfies the three statements within m epochs. Okay. All right. Now let's say, then the question is, how can we construct the model without training data? So in that case, if the input is all y are z and all x are y, this means the network should construct 3 circles to satisfy 2 relation. So if currently the red circle is outside the green circle, then the network should transform it inside the green circle. So it should inspect what is the current status, and then it should know what kind of operation or what kind of gradual descent process it should take to reach this target. So in that case, you just need to shorten the distance between the central point and reduce the radius. Okay. So in that case, each syllogistic statement corresponding to a predicate, a spatial predicate. And this spatial predicate can be observed as computed by the network. So no VRW means V circle and W circle are disconnected, means the distance between a central point is greater than or equal to the sum of their radius. All VRW means the radius of V plus their century distance to the central point should be less than or equal to the radius of the radius of W. Some VRW, there are 3 situations, but this is corresponding. What's missing is that V and W, they are not disconnected. So we just negate D. Okay, so that we establish one-to-one mapping between syllogistic statement and spatial relation. The same for some W are not some V are not W. It means the V sphere is not part of the W sphere. So negation P. Then if suppose the current target is all VRW, and currently they are disconnected. So what we should do is to reduce the distance between a central point or reduce the radius of V or increase the radius of W. And this means we can define such kind of loss function. Okay. This loss function equals 0 if the target satisfies. It's always greater than 0 if the target relation is not satisfied, and it's gradual descent. Okay, when this loss function reduces value, then it's a step degree, the V sphere is always moving inside the W sphere. So if the target is no VRW, they should disconnect, then we can do similar. We define a loss function. If the target status satisfies, the loss is 0. If not, it's greater than 0. And we define it as a gradual descent function. Okay, it seems that is independent of the current status. We can do the same for some VRW. It's just we do in a similar way. If the 2 spheres are not disconnected, the loss is 0. Otherwise, the loss is greater than 0, and we define it gradual descent. And for the target is some V are not W, we define a loss function. It reaches 0 when V sphere is not part of W sphere. But here we have a problem. For example, if the inspect model look at the green circle inside the blue circle, it can be some VRW, or it can also be all VRW. And the same, if the two spheres are disconnected, it also can observe two cases, some V are not W or no W are V. Even worse, if the blue circle is properly contained by the green circle, it can be two status, either some V are W or some V are not W, or even all W are V. And what does this mean? This means the problem here is that what we observe is different from what is a target. What we observe is always positive relations, but here we have two negative relations. Actually, the negative relation is deduced or inferred from the positive relation. So, okay, we can only observe positive relations. This means we should specify all the positive relations, and that's the relation that our model can inspect. Okay, and then the target relation is required by the task. So here we have 5 positive relations, say disconnect, partial overlap, and then proper impact, and proper contain, and then equal. Okay, these can be observed. And the target for syllogistic reasoning, we have 6 targets. The disconnected, one contain the other, and negation. So then the loss function is always observe a positive relation and keep in mind what is the target, and the loss function should translate the current observed relation to its neighborhood and towards the target. And this neighborhood transition introduces a map. Okay, suppose here the current state is proper part. If the target is disconnect, so we can easily write a loss function. There's a from proper part to disconnect. But if we really gradual descent to reduce the value, it would first reach the partial overlap relation. And then from partial overlap relations using another loss function, starting from PO to D. And these blue loss function, we call it atomic, the neighborhood. So this means when we apply these transition, they should not either stay to the current status or reach the target. It cannot move to a third relation. Okay, then the network's behavior is deterministic. So totally we can design all these atomic neighborhood transition. Question is, are they really atomic? It looks like that. But we remember, when we change this sphere, the update of the central point and update of the radius, they are independent. So it can cause problems. The question, are these atomic transitions atomic? Answer is not all of them. And there are some problematic situations. Let me show you the case. Suppose the green and the blue, they are partially overlapped. And then we want to make them separate. This means we should either increase the distance between a central point or to reduce the radius of the green of V. Let's fix one of the sphere. Okay. Let's see what happens. If the radius reduces too fast and moves slowly, the green will be inside the blue. That is, the status go to the upper part. And this situation, this means this transition is not always atomic. The reason is when the center of the green is inside the blue, there'll be problem. So the solution is that we distinguish two kinds of partial overlap. One is the center of the blue, the center of the green is inside blue, and the other is the center of the green is not inside blue, is either on the boundary or outside. And in that case, no matter how we change radius and increase distance, central point, the transition is atomic. And when the center of the green circle is inside the blue, it may cause problem. In that case, we fix the radius of the green and only increase the distance between central point till it reaches the boundary, till the center of the green circle reaches the boundary of the blue. And then it just move to the P01 case. Then this transition is atomic. Okay. And the similar case is from PO transfer to the green contain blue. The situation is quite similar. The operation is to reduce the distance between a central point or to enlarge the radius of the green circle. So let's fix the radius of the blue. It can happen that the radius of the green circle enlarged too slow, and they move to the center too fast. They become inside the blue instead of contain blue. And this situation happens when the radius of the green circle is smaller than the radius of the blue circle. So we decompose this PO relation into two cases. One is that the radius of the green is greater than or equal to the radius of the blue circle. In that case, the transition from PO to inverse to containment relation is atomic. Okay. If the radius of the green circle is smaller than the radius of the blue circle, we first enlarge their radius and fix the central point. Okay. Here's another case. So if the current state is the partial overlap, it always causes problems. So the last situation is if the target is proper part of green is proper part of blue. The operation is to reduce the central point, reduce distance between the central point, or reduce the radius of the blue. When the size of the green circle is large, 2 times greater than the radius of the blue, and if they move very fast, it can contain blue instead of inside blue. Okay. So in that case, there's no better solution if we only using gradual descent. The easiest solution is that we just set the radius as equal to the blue radius. We don't need gradual descent. But if we do gradual descent, then it may goes to the containment relation, and then another map will you go back to the purple part by reducing the radius. And there's a loop to make the radius of the green circle smaller and smaller and smaller till it's inside green circle. Okay, so neighborhood transition, although it appears very simple, in reality, it's quite complicated. So we can remove this non-atomic transition, and we can remove also this targeting the equal relation because it seldom happens. And then this transition is not always atomic. Then we specify this network into this status with only one exception. The red transition may not be atomic. All the other transitions are atomic. So in this way, without using training data, we're just using this transition map, we can construct a model in the embedding space. And the out of distribution phenomenon can be avoided. So let's look at an example. Let's take one sentence. Suppose we want to construct a model that Y circle is disconnect from Z circle. And this is the current status. So currently, the green circle contains blue circle. The target is the disconnect. So we first observe the PP relation, the purple part. Y is purple part of Z. Then the loss function is from purple part to PO. Okay. Then this means it will increase the century between the increase the distance between a century point, and also reduce the it's not just increase the distance and reaches to the PO and PO2, and then from PO2 to PO1, so that the century is outside the blue circle. The century of the green circle is outside the blue circle. Then using PO1 to D, in that case, the radius and the century updated simultaneously. Here they separate. So that is, the model is constructed guided by a map, not by training data. Okay. So I think that's today's topic. The next talk, I will talk about the control process to construct at least three statements or syllogistic reasoning with a loop with n terms, and need to prove that this process guarantees that as long as there is a model, it only needs one loop. Okay, this means we need to prove m equals 1. And this is based on the control process and the map, not by training data. I think so let me summarize this talk. First, we have limitations of supervised deep learning. There are 4 limitations. And then we need to introducing a neural network. We call it sphere neural network, means we enlarge this vector embedding into sphere, using sphere to represent concept. And then reasoning is not a mapping from premises to conclusion. Rather, it is decomposed into a model construction and model inspection. Okay. Then we can remove these three of the obstacles. What's remaining is the OOD, the out of distribution problem. And then we need to say the criteria to achieving deterministic reasoning is that if there's a model, it should construct within m steps. And this is achieved by the map. In that case, we remove this obstacle. Okay. So I think next topic just to prove it should a complete process to arrange all these spheres in one epoch. And this is a quite challenging talk. Yes, any questions or unclear about that? Yeah.
Is it true that like every sort of like logical statement can be represented as spheres?
Yes, I will. After next talk, I will talk about how to promote this sphere embedding to other logical reasoning. Because if we say here we only have part whole and disconnect, if we think about conjunction and disjunction, and then we need to represent a complement set. Okay, we have, if a predicate is corresponding to a set, then the negation is complement set. And then in that case, we need to define the sphere on a circle. So if the universe is a circle, and sphere is an arc. Okay, then the complement is also an arc, and it's closed. So in the end, it's like a rotation of an arc. As for construct a model for general logical reasoning. Yeah. And we can also argue that the degree of overlap can represent Bayesian formula. So that is, this arc embedding can unify logical reasoning and statistical reasoning.
Spheres or circles, we have to be like 2D circles.
No. For this syllogistic reasoning, we tested from 2D to 10,000D. It's the formula is the same. I mean, you just the difference is the distance is the computed in n-dimensional space. Radius is just a constant. What the effect is there's not much computational increase if we increase dimension. Okay, hard thing is the proof. And that's the. So let me stop recording. Any questions?